So yes, my talk is about quantum machine learning and how can we use it. And I'm a research scientist at Zapata Computing. I'll tell you more in a little bit. And since we're in Romania, I couldn't resist but showing a picture of me in front of the Palace of Parliament. I went to Bucharest and Transylvania in my teenage years, many years ago, and had a wonderful trip. So here I'm in front of I think it's the record of heaviest building in the world, right? And biggest in terms of base. So yeah. Just thought I'd show it.
Yeah.
Yeah. Cool. So yeah, basically as we've seen in other talks, the same way that all roads lead to Rome, all industries are leading to quantum computing. Pretty much most applications are finding their way in quantum computing and finding ways to improve it. So I'll tell you about a couple today. And where I work is called Zapata Computing, and I invite you to check it out. I'll give you some links later where we have a platform for quantum machine learning. So it's for quantum computing. So it's a platform for business and companies and research institutions to be able to run their code on pretty much any quantum computer that's available today, and also in classical computers and in simulators. So yeah, I'll give you more info later. So what I'll show you today, well, I'll tell you a bit about what quantum computing is. This is probably going to be the most elementary talk in this conference, but there'll be a few things that I'll introduce, but I'll get to some cutting edge research things by the end. And I'll tell you a bit about generative machine learning, because this is the one that we are tackling currently, and I'll tell you why. So I'll tell you about quantum generative machine learning. And this I won't get to, but I'll give you links to a coding lab in Pikeville where you can follow what we did today. And I'll also give you a link to a demo of Orchestra, which is the platform that we have at Zapata, so you'll be able to play with it. So first, what is generative machine learning? It's sort of one of the most cutting edge versions of machine learning right now. So what is machine learning? And allow me to go super basic here, but in machine learning, in supervised machine learning, you have a labeled data set, for example, images. And then what you do is you show that you train the model with this labeled data set. The labels are the names of the animal, and you show it an unlabeled data point, and the computer guesses the label. That's supervised machine learning. So it's basically answering questions. What is unsupervised machine learning? Well, here you have no labels, so you have to the computer has to guess things that are not given to it. So instead it will just say, well, I think I cluster these ones and they are this type, and these ones are this type, etc. And in generative machine learning, it's a type of unsupervised machine learning, but the opposite happens. You instead of the computer answering questions, you give it the label. You say, draw a dog, and the computer goes, boom, here is a dog. This is an oversimplification, but it's just to show you that in general machine learning, the computer is not answering questions. It's building, painting images, writing poetry, creating music, even creating solutions to problems, as may have the chance to show you later. And the difference between classical and quantum is not that different. Pretty much in very high level terms, how does a classical general model works? Well, in some way, you the classical one you have in any neural network or in any model, you have numbers coming in and numbers coming out, and those numbers you turn into your image and you somehow compare it to the data set. And in a very machine learning approach, you go and update the parameters of your neural network, right? Quantum general model, same thing. The way you apply these numbers in a neural network is by just simple operations: addition, multiplication, sigmoid, ReLU activation functions, etc. And a quantum neural network is the same, except you have qubits, right? You have qubits that get operated on each other. Image comes out, and then you compare it to your data set and you upgrade these parameters. What happens with qubits? Well, in the same way that with numbers, you add them, multiply them, etc. With qubits, you do things like rotation, do things like entanglement, quantum gates, etc. But it's pretty much the same concept. You know, in machine learning, you try to get what you want, and in order to get what you want, you play with parameters. Well, in quantum machine learning is the same thing, except that you have what's called a quantum circuit, and you play with the parameters of that quantum circuit so that when you get your output, you get what you wanted. And so now here's a question. Why do we care about quantum? Why do we care about general models? Why don't we go for the easy stuff? Like, why don't we try to do supervised learning with quantum computers, and there is a lot of work on that. But one reason is that it's done very well in classical computers. I mean, supervised learning is done quite well in classical computers, and it would be hard to see great speed ups or great advantages. If you make linear regression work faster, nobody will notice, right? However, there are a lot of advances. Whereas in generative models, there's a lot to fix, not just in speed, but also in performance, in looking for things in distributions, etc. But my favorite reason why I care about generative models is because it's the strength of a quantum computer. A classical computer is very good at deterministic things like adding numbers or applying functions, right? With an input and an output comes out. Classical computers are not so good at generating random numbers. As a matter of fact, they can't. All they generate is pseudo-random number. Classical computers, like a really boring person, everything they say is scripted from a formula. They can't really say random things. So we can make them look random, but they're not random. Whereas a quantum computer is fantastic at doing random numbers. They can generate true randomness. So for generative models, you want to generate random stuff, right? So for a classical generative model, you have to cook up a random input, fake it, and get a random output. Whereas for a quantum circuit, you can get functions that just spit out random stuff given the same input, right? It's called measuring. Quantum measuring gives you a completely random thing, as long as you're able to teach it the right distribution. So here's the problem: classical generative models, you have to sample random stuff as the input, and that is sometimes hard to fake. They do very well, but that's a big bottleneck of classical generative models that we don't have at quantum. Okay, so let me give you a laundry list of generative models. The classical ones are GANS, generative adversarial networks. There's restricted Boltzmann machine, variation autoencoders, and many more. For the quantum ones, we have quantum everything, basically. Quantum generative models, quantum Boltzmann machines. And the one that I'll talk about today is called quantum circuit-borne machines. So I'm going to show you an architecture of a generative model that works on quantum computers. And we're going to go over it in a fair amount of detail. So Vlad, if there's any questions so far, I'm happy to answer them. Otherwise, I can go with what is quantum computing.
For now, no, there aren't. I think everybody's just trying to to grok what's going on in there.
Sounds good. If anything is not clear, by all means, please put a question in the chat, and I'll be happy to elaborate. If we go on a tangent and do different topics, fantastic. It's I'm here for to talk about what wherever you guys are interested. So let me talk a bit about quantum computing. So let's go to the very basics. What's a qubit? So what's a bit, right? A bit in a computer is I look at it as a switch that's on or off. It's a yes or a no, and computers are made of those. Well, and for the purpose of this talk, 0 is always red and it's always up, and 1 is always blue and it's always down. And so what's a quantum computer? Well, we can see it as a slider. A qubit can take every value from 0 all the way to 1, and it can have a superposition, half, 0, 1, and a little more 0 than 1, and a little more 1 than 0, 70% 0, 30% 1, etc. So basically, anywhere you are on this slider, you can have. So it's already a lot more information than a bit, right? It's already infinitely many. And there's even more. Actually, the switches don't look like sliders, but they look like an entire sphere. So imagine if your switch was a sphere, and in the sphere, basically any direction that you point in any direction that you can point your finger at is a different qubit. So basically any point in the sphere is a different qubit, and based on the height of that point, you're on or off. So if you put it on very high on the North Pole, you're in complete 0 state. If you put it on the South Pole, you're in 1 state. And if you want to have a perfect superposition, 50%, you can pick any point in the equator. So there's many ways, infinitely many ways for a qubit to be in 50-50 superposition, and there's infinitely many ways to be in 70-30 superposition and anything. So it's just a lot more information. The way I'm going to write them in this talk is sort of like vectors, right? I tell you how much percentage there is up and how much percentage there is down. And in reality, to be fully technical, they're square roots. So I want how much square root of two numbers that add to 1. So it's two numbers whose squares add to 1, and that's how the qubits are going to be represented. When I like to ignore these square roots when I don't need them for math purposes, so I just put on my green goggles and I don't see square roots. So if you want to ignore square roots for pretty much the entire talk, you can just know that they're there. And one reason there's square roots is that we have I'm showing you all these numbers, but for example, what do you think would be the point that's closest to us? What do you think? Let's see if anyone in the chat wants to tell us what they think this point is. If we have root 5 on the right and root 5 minus root 5 on the left. Any takers?
None yet, but that might also be because we have a slight delay, something like 30 seconds, so we're not in real time, but we do have a question.
Yes, please go ahead.
Wouldn't the training process of classical networks benefit from quantum computers?
Absolutely. I'll have the chance to tell you a little more at the end, but yes, we can train. So mostly quantum algorithms work enhancing classical algorithms, right? So you're not going to find a fully quantum algorithm that begins quantum and ends quantum. A lot of them are just a classical algorithm, and there's a bottleneck somewhere. And in that bottleneck, you help it with a quantum part, like Shor's algorithm, right? Like it's purely classical number theory. Somewhere there's a part that takes forever to search. Use a quantum computer for that. So in the same way, a lot of classical machine learning is like that. We insert a quantum little part into a neural network and make it work better. All right, so because of complex numbers, this is going to be root 5 I root 5, or it's a root of -1. I'm going to avoid complex numbers during this talk for the most part, but just know that any point in the qubit is a pair of complex numbers whose squares add to 1. And normally it's written like this, the wave function, which is how much of 0 plus how much of 1. But I'm normally going to write it as this little vector on the left, which has the quantities on the side. So for fully general terms, it's two complex numbers whose squares, modulo squares add to 1. But actually, for technical reasons, we can always afford the first one to be real and non-negative. The reason is the phase change. But as I said, let's pretend they are both real numbers. So during this talk, representations of a qubit, I'm going to have a point in the sphere, which is called a Bloch sphere. I'm can also represent it by arrows, by vectors, and by the wave function. So here's another one. Here's a point in the equator. Here is some random point in the southern hemisphere. And here is the South Pole. So most of the time I'll use either a Bloch sphere or vector notation. And again, feel free to stop me if anything's not clear. So some qubits are special. The special ones are North Pole, South Pole, and the two sort of perfect superposition states, which we're going to call plus and minus. Now, here's something interesting, right? The bit carries one bit of information, a 0 or a 1, and the qubit carries two complex numbers. So in this complex number, for example, in the number on top, I could easily fit the entirety of human knowledge, right? I have a real number which goes on forever. I could fit in books and books of information there. So what's the catch, right? It seems like this is too good. There is a catch, and the catch is measurement. And what happens is that the very moment I look at a qubit, I lose all the information it has. So if I have a qubit in that position and I look at it, then two things can, and this qubit is 70% up, 30% down. Two things could happen, right? It could go fully up, or it could go fully down. And with the 70% probability it goes up, for the 30% probability it goes down. This is unfortunate, but it's how it is. The way we look at it in quantum circuits is like this: you pass the quantum circuit, and it's come out like two magnets. One of them ends up winning, and then you go like this. And if I run this experiment many times, I'm going to notice that 70% of the time it goes up, and 30% of the time it returns an up, or it returns a down. So that's one quantum gate, and there are more quantum gates. So in classical computers, we have classical gates, for example, the NOT gate, which goes from up to down, right? It flips the switch. If I had a 1, it becomes a 0, and if I had a 0, it becomes a 1. Well, in quantum land, we have the same thing. Just imagine operating on the sphere. So if I have an up, I can rotate the sphere 180 degrees and I get a down, and I can rotate it back up. That's a quantum gate. So because a sphere can be rotated under 3 axes, X, Y, and Z, then basically any rotation is a quantum gate. So if I rotate theta degrees, theta radians on the X axis, I get this rotation gate. If I rotate on the Y axis, I get this one. And on the Z one, I get this one. So imagine, again, qubits are spheres, point in a sphere, and I can rotate the sphere and the point can go anywhere, and those are my operations that I do. Okay. You can look at them on matrices. I don't always look at them on matrices unless I really need to, but if you are to operate on the vector, these are the corresponding matrices. So for example, if I pick the right angle, I can get something like this. And if I operate in my vector, where I have the amount of up and the amount of down, I get something different. So this is the matrix that sends me the North Pole all the way down to the South Pole. And so there's another one called the Hadamard gate, which is the one that sends 0 to the plus superposition state, plus to the South Pole, this one to the minus superposition state, and this one all the way back to the North Pole. And basically the matrix for that one is this one. So if I operate it on the North Pole, I get the point in the equator. So here is the easiest generative model that we can come up in a quantum computer, is simulating a coin toss, right? So if I want to simulate a coin toss, I simply operate in my qubit, I rotate it 90 degrees, and then I sample, I measure. And if I measure with 50% probability, it can go heads up, or 50% it can go down, which is tails. And if I run this experiment many times, I'm going to notice that roughly 50% of the time I get heads and 50% of the time I get tails. Simplest generative model we can invent, right? It creates a Bernoulli distribution. How do I do a biased coin toss? If I want a coin toss that I can cheat and get 70% of the time heads and 30% of the time tails, well, I simply rotated the right amount. And the right amount, I think it's this, a 2r cosine of 0.7. If I rotated the right amount so that the point is 70% of the way up, then when I measure, it's gonna go up with 70% probability and 30% probability down. So I have been able to simulate my coin toss, my biased coin toss. So I can generate every single biased coin in a very simple quantum circuit. It's a good time to check if there's any questions in the chat.
No, but we have an answer for the previous question, which was 0.5 and 0. But yeah, we've seen.
Fantastic. Thank you. I'll still receive questions since there's a lag, and in the interest of time, I will sort of answer my own questions, but I still welcome answers and comments all the time. So thank you. All right, so let me tell you a bit about entanglement. So if I were to talk about quantum qubits without entanglement, it would be like talking about, I don't know, humans without talking about human interaction. It's the building block of everything, right? And entanglement, I like to see it in a probabilistic way. So I like to see it as like, imagine we had 2 people, and the 2 people can be happy or sad with 50% probability. So 50% happy, 50% sad. And so if these people have never met and don't know each other and don't influence each other, then what are the probabilities of both being happy? Well, they're independent, so it's 25%, right? 50% times 50%. Happy, sad, also 25%. Sad, happy, 25%. And sad, sad, again, 25%. This is when 2 people don't know each other. Now imagine that these people are happily married. And so when one of them is happy, the other one is automatically happy. And when one of them is sad, the other one is automatically sad. Then we ask one of them, we only need to ask one of them if they're happy, and then the other one, we know what they are. So those probabilities change. They're no longer 25, 25, 25, 25. Now they're going to be these two are 0, and these two become 50. So now we have 50% both happy and 50% both sad. So we say that these people are entangled. Same thing happens with qubits. If I have two qubits that can be on superposition 50-50 up and down, then four things could happen. That if I measure them separately, they're both up, or they're up down, or down up, or down down, with 25% probability. I'm going to write this like this. So this is an important notation I have on the right. I'm going to consider the vector of all the possibilities that two qubits may have, and their probability on the right with the square root. Now, what happens? This is a very important thing happens. Sometimes I can entangle qubits. This is done in a lab, and it's quite complicated, but I can entangle qubits in such a way that if I were to observe the one on the left and I get up, then I don't need to observe the one on the right, because it already is up. Like if I were to observe it, I will always get up. I'm never going to get up down. So the probabilities change from 25, 25, 25, 25 to 50, 0, 0, 50. So we say that these two qubits are entangled, and this is called a Bell state. Now, there's many other ways they can be entangled. This is the strongest version of entanglement. But basically, that's the concept, right? So let's do I say quiz, but I'll feel free to answer on the chat. But I'll go ahead with it. If the first person is happy 70% of the time and sad 30%, and the other one is happy 60% of the time and sad 40%, and they don't know each other, they're not entangled, what are the probabilities for both happy? So for that, I would multiply them, right? It would be 7 times 6 is 42. The next one is 70 times 40, which is 28. 30 times 60, which is 18. And 30 times 40, which is 12. So if the people don't know each other, these are the probabilities, right? They're independent. So if I have two qubits that are not entangled, their tensor product, and the tensor product is the combinations of all the probabilities for their ups and downs. It's simply the combination of the four products of the independent probabilities, right? So I'm going to use this notation a lot, tensor product. And when I have entangled qubits, for example, these two are not entangled, but if I have anything different, if I have anything that doesn't satisfy this nice property on top, that is the product of independent probabilities, then I have entangled qubits. So this one I can write it like this, but this one I can't. And the way to tell is that there are no numbers such that if I can do the operations on top, 7 times 6, 7 times 4, etc. I don't have that in the bottom. And a way to check is if the product of the first and the fourth is equal to the second and the third, then they are not entangled. But if they're not, then they're entangled. Okay. So basically, if measuring one qubit affects in any way the outcome of measuring the second qubit, even if it's by a tiny percentage, they are entangled. And if it doesn't, then they're not entangled. So I hope that's clear, but if there's any questions, feel free to ask them in the chat. And now there are entangling gates. So gates that will entangle our qubits. And the way they work is in the same way as normal gates. We have and or are the classical gates. I'll go quick over this because you know them already. And in the quantum land, we have, for example, the CNOT gate. So the CNOT gate is controlled NOT. And what this one does, if you look at it carefully, the first one does nothing. And the second one, sorry, if the first bit is an up, then you do nothing to the second bit. But if the first bit is a down, then you flip the second bit. So in other words, if this is the tensor product, the CNOT does this. It just flips the bottom two. And that's the CNOT gate. And if you look at it as matrices, this is the matrix that flips the last two. So that's one that if you give it something, it entangles the qubit. So the two Bell states, the two most entangled states are these two. The one where with 50% probability I get up and 50% I get down, and the one where 50% probability I get up down, and with 50 I get down up. So I'm gonna write them like this. I'm gonna sort of forget about the zeros. So here's the question. We we did simulate a coin toss, we can also simulate an entangled state. And so this would be like this. We start with up, up, and we want to end up with half up, up, and half down, down. So in other words, what I'm doing is simulating tossing two coins, but these coins have the special property that I always get either two heads or two tails. I never get heads, tail, or tail heads. And we're going to build a circuit that does this. So the way we build a circuit that does this is by using a Hadamard gate and a CNOT gate. So let me show you. We have our qubits in the initial position, which is all of them in North Pole. And we applied a Hadamard gate. So this rotates one of them 90 degrees. And then we end up with this. The first one is half-half, and the second one is 1-0. And the tensor product, which is all the probabilities, gives us this. And then we apply the CNOT gate, which entangles them. This is the way I show entanglement. And remember that the CNOT gate, what it does is flips the third and the fourth. So we've been able to entangle these two qubits. So that's the way we entangle two qubits. And it goes from here to here. We can also do it quicker if we look at some matrices called XX, YY, and ZZ. I'm not going to get into the details, but these are these type of matrices that if you pick the right angle, it will entangle them. So think of it as like just a gate that if I come in with two unentangled qubits, what comes out is entangled. And these are the matrices for the X, Y, and Z. They're called Ising coupling gates. Okay, so that's enough on the quantum computer. Let me get into what is quantum machine learning. So the quantum circuit born machine is the architecture that I'll show you. And so let's imagine 4 qubits. I have 4 qubits that can be all of them in up or down. So I have 16 possibilities, all the way from up, 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 all the way to down, 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 to the 4 possibilities. And any state looks like 4 numbers, 16 numbers whose squares add to 1. So I'm going to write them like this. And what we're going to do is it's actually very hard to find the circuit to create any state that you want. So for example, creating a Bell state, which was simulating a coin toss, was easy with a Hadamard gate. Creating a Bell state with 2 heads and 2 tails was slightly harder. We needed a Hadamard and a CNOT. How would it be to create a Bell state with 3 qubits, right? That's much harder. And how would it be to create a Bell state with 4 qubits? Like actually figure out what circuits to put, what gates to put where, so that what comes out is either all up or all down. That's quite complicated. And as you can imagine, the more qubits, the more complicated. So for that, we're going to use machine learning. We're going to use a QCBM. And the way we're going to do it is a very machine learning way. So for 1 qubit, we want something that comes out that is half-half. And so if we pick a random angle theta, something comes out, A and B. And all we have to do is play with this angle in order to get the A and B that we want. So that's with 1 qubit. Well, 2 qubits is the same thing, right? We have an entangling gate. We get some numbers A, B, C, D. And we want to go from up, up to half up, up, half down, down. So all we have to do is play with this angle so that it gives us what we want. And for 3, we do the same thing. We want to go from up, up, up to half up, 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 half down, down, down. We have 3 angles. We're going to connect the first and the second, the first and the third, and the second and the third, and try to play with these 3 angles. You know, you can see the machine learning happening, right? In machine learning, you play with parameters to get what you want. Well, here we play with angles to get what we want. And how would you do it for 4 qubits? Well, this is what is called a QCBM. So we have certain architectures that are fixed architectures with a bunch of angles, and we want to try to find the right angles that help us get to where we want. Vlad, how am I doing with time? Just to get an idea.
You're good.
I can keep going.
So, yeah, sure, sure.
I mean,
yeah, we will have a scheduled break at in 15 minutes.
Okay.
So there's at least 15 minutes to go.
Okay. Okay, sounds good. I'll go for 5 to 10, so we have a few questions. Question time.
Sure.
But feel free to stop me if I'm going too much. So the paper I'm going to show you is a quantum. This result is called a quantum circuit-borne machine, and here's the reference. And basically, it works like this: you have a fixed architecture with a bunch of parameters which are angles. You find the right angles so that when you put in 4 qubits in the up position, what you get at the end is qubits on the position that you wanted. And that's what it feels like machine learning, right? So the way I look at it is you have your 4 qubits, your single gates will rotate these qubits on the y-axis and on the z-axis, and then you start entangling them by some angle. Then you entangle them a little more, and then you entangle it a little more, and then you entangle them more, and then you measure. So when they measure, they go either up or down, and then you record what you got. So here we got up, down, down, up. So I'm going to say that this circuit sends up, 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 up to up, down, down, up. Okay. And if I run this many times, the idea is that let's say that I want to get this state. This is the state that I want to build. So this state, if I run it many times, I want to get this. This is the histogram of the numbers you see on the left. Now, if I were to run this qubit once and I get, for example, down, up, down, up, if I run this circuit, I get it here, I record it here. If I run it again, I get another random state out, then I put it here. And if I run this many times, the idea is that I create a histogram. And so all I have to do is I have to find the right angles to create the histogram that I want. So I want to create the histogram that half of the time I get 0, 0, 0, 0, and half of the time I get 1, 1, 1, 1. And so if I run this circuit many times, I would love to get that histogram. So now I start with random angles, and the random angles give me some histogram, probably not the one I want. This is the target one. This is the one that I really want. And so what I do is I compare them. And once I compare them, I'll show you how to compare them later. Then I use that to update the angles in my original circuit. So this is pretty much the way you train a neural network, right? You put an input, you see what you get out, you compare to what you wanted, and then you use that to update the parameters. So if I do this many times, I start getting a little better. I compare again, I update the angles, and after many, many, many iterations, I'm gonna get what I want. So that's called the training process, called data-driven quantum circuit learning. So basically, I start with my circuit, and I end up with a much better circuit that gives me the distribution that I wanted. Oops, sorry. So in the lab that I'm going to show you, that I can send you the link later in the chat. It's this one. It's called tutorial ODSC QML and the Zapata Computing GitHub. You can see 3 examples. One is training a fair biased coin toss. The other one is entangling a state, and the other one is running a quantum circuit-borne machine. And the data set that we use is bars and stripes. So we have the bars and stripes data set is sort of a toy data set that you can play to generate. And it's basically all day in a rectangle. Take any bar, any combination of bars or any combination of stripes, including the entire thing or none of it. And the way we show a bars and stripes is by calling one color 0 and one color 1. So for example, this one is 0, 0, 1, 0, 0, 1, 0, 0, 1, which we write as up, up, down, up, up, down, up, up, down. And so for this entire bars and stripes data set for 4 qubits, we have, these are the 16 possibilities, right? And out of those 16, only 6 of them are bars or stripes. And so what we want is to create the distribution that gives us 1/6 probability each of the bars and stripes, and with 0 probability anything else. So we want to create this state, which can also be written as the state. And that can be done with a QCBM. We start with a random, with a circuit that gives us a random state, and end up with one that gives us what we want. So let me tell you a little more about the training process. So the first one is the loss function. So I'm going to tell you how to compare two distributions. So the distribution in the left and the distribution in the right is sort of, this is the equivalent of a neural network error function, right? And the way we compare it is with KL divergence. So KL divergence does the following. If you have some distribution, and I'm going to compare it with a distribution that is similar, I want KL divergence to give me a small number. And if I have a distribution and I compare it with a distribution that is very different to it, then I want it to give me a large number. And KL divergence is simply this formula, summation of P of X log P of X over Q of X. That happens to be a big number when the distributions are different and a small number where they're small. So that's the error function that we're training our circuit, our quantum neural network on. And now I'm going to show you how to minimize a function, right? Because I promised I was going to tell you how to update these angles. Well, the way we update them is by minimizing the KL divergence between the target distribution and the one that we're getting. So there are two ways. Well, there are many ways. It could be gradient methods or non-gradient methods. I'm going to show you one of them, which is particle swarm optimization. So here's something interesting. When you train neural networks, you can train them using derivatives, right? You can calculate the gradient and then of the error function and then walk in the direction of the gradient. This can also be done in quantum circuits by taking derivatives, like the derivative sine is cosine, etc. But there are many non-gradient methods, and I'm going to show you one of them. Basically, non-gradient methods they try to minimize a function without taking derivatives. And the way they do it is by, if you want to, for example, minimize this function, which is the lowest point is this point, a blue point over here, then you just get a bunch of your friends and make them walk around the space in some probabilistic optimal way in order to find that minimum with a high probability. So I'm going to show you particle swarm optimization. And let's say that this is our space and we want to find that point here, which is the minimum value of our function. So high is white and yellow and black is the low points. And we want to find that point. So here's how particle swarm optimization works. I'm going to put a bunch of dots in the plane, and those are my friends, not in the plane, but in the surface. And let's imagine that we're all walking around trying to find that minimum spot and we're talking to each other. So I'm going to give you three strategies for finding the minimum. The first one is inertia. The second one is personal best, and the third one is team best. And each one of them is not a very good strategy, but combined, they're very good. So the best strategy is to combine them. So the inertia strategy says, okay, you're walking around, now stop where you are and look at the direction where you were going and continue walking in that direction forever. Okay, that's okay, right? You now check which is the best point that you arrived as a team. So that's an okay strategy. The second one is personal best. So it says, remember, where was the lowest point that you have reached yourself? So let's say that this point has reached this one in the past. And so each point has its own personal best that they've reached while walking. Well, they can all walk towards their personal best. And as a team, where's the best point that we got? Let's say it's over here. And now the third strategy is team best. So let's say we talk among each other and we figure out where is the best spot that any one of us has arrived. And let's say that this was the team best. So we all walk towards the team best and until we leave the space. And as a team, the best we did was this. So those three are not very good strategies, but if you combine them, they are. So let's say that we're going to take one step in the inertia strategy, the direction that we're walking towards, one step towards the personal best, and one step towards the team best. So this is vector addition, right? I take one step in inertia direction, one step in personal best, and one step in team best. And imagine that we're all doing that. So at every step, we're all doing that and talking to each other to figure out what the personal bests are, what the team bests are. And it's believable that this is a good way to explore the space, right? So with a high probability, you'll get to the minimum or at least a very good point. So that's particle swarm optimization. So that is how we update the angles. And so that's pretty much the training of the neural network, right? You start some random parameters you always update you see what distribution you got, you compare to the one you wanted, and you update the angles. Let me jump a little towards the, whoops. Let me jump a little towards the conclusion. Yeah, let me tell you a bit about the applications. Basically, one thing that we do is use them in generative neural networks. So generative neural networks are the ones that generate images. So all these faces of people are images that don't exist, that's generated by a neural network. So here's a paper of generating high resolution handwritten digits. And what they do is the following. If you've seen a generative neural network, adversarial neural networks, what they do is from a latent space, they pick a point, they have a generator and a discriminator. And you pick a random point from a latent space and you generate an image using the generator. And then you train the generator to build images, and you train the discriminator to tell these images apart, noise or image if they come from the real data, right? So the discriminator, if it takes an image from the generator, it says it's noise, and if it's from the discriminator, it says it's an image. And as you train these two, they both get better. The generator gets better at creating good images, and the discriminator gets better at telling them apart. It's kind of like an art forger and a critic. And then one day you'll be able to generate good images. However, there's a problem that these have, which is that you don't know what the latent space is. And if you pick random points out of the small latent space, you may get good images or bad images, because what you're doing is you have to fake a random input, and that's not very good. So what we do is we look at that latent space, the space where the prior comes in, and we try to mimic it from the last layer of the discriminator. We say, okay, where are the data points going? And let's say they're going here. And now what we do is we use a quantum generative, a QCBM to model this space on the right, and then we pass it to the left, and then that gives us the best spots to pick points from the latent space, and that has shown advantages in training generative neural networks. So as you see, most of the neural network is classical, but there's a small step where you help it pick stuff from a latent space using a quantum generative model. And I think I'm out of time, so I'll go ahead and put my final slide. Well, actually, I'll tell you a bit. I'll give you some links. These are check this orchestra.io docs to see more of Orchestra, the product that we have that you can run workflows in quantum computers. And finally, I will give you some of my data. So as Vlad mentioned, I have this book called Rocking Machine Learning, which I'd love to give you a 40% discount code over here. This is the link, and this is the 40% discount code. And yeah, if you want to follow me, here's my channel, here's my Twitter, and a page with all the information. It's called serrano.academy. So thank you very much. Sorry I went a little over time, but thank you, Mulțumesc. And if you have any questions, I'm happy to answer them.
Thank you, Luis.
Yeah, I would say it was a bit over time, but it was well worth it. So I really enjoyed it, and I hope everybody out there did the same.
Thank you. Thank you very much.
Absolutely.